Well, thank you very much for the kind introduction and also for making us possible to give this presentation today here at Quantum Korea. So as already said, my name is Moritz Kirste. I work for the company CHIRIHI Instruments, and I would like to talk today about how we enable the second quantum revolution with classical instrumentation. Now, CHIRIHI Instruments has a quantum mission, and what we call our quantum mission is, first of all, we accelerate the second quantum revolution, and we help to build quantum computers. And now you might ask yourself, how do we define success on our quantum mission? And I can show you a picture how we define success. So you can see here two of our researchers or of our customers, and they're here in the lab, and they look into this photo very happily. And the question is, why are they looking so happily into the camera here? The reason is they've just published one of their Nature papers. And that is how we define our success. So when we can let our customers focus on their main tasks, then we see our quantum mission to be successful. Now, what are the solutions we provide in quantum computing? We are an instrument provider, so we provide control electronics. We provide so-called quantum computing control systems. So that means we provide solutions for the qubit control. And here, for example, we focus on maximum gate fidelity. Then we provide solutions for the qubit readout. Again, here it's about fast, high-fidelity qubit readout. Third, we provide solutions for doing quantum feedback. So when you're looking into systems of much larger scale than just a few qubit numbers, then we have to talk about good feedback solutions. And last of all, we provide something which we call the system control. So that means we want to provide a solution where customers can use the full system as programming one unit of a quantum computer. And in the end, we solve anything you want to have regarding interfaces and connection between those instruments. Now, there's also a possibility to combine these abilities into one instrument. And one example of this combination of abilities is the so-called SHF-QC. So that's a qubit control readout and feedback now in one instrument. And this can control up to 6 qubits at once. Now, let's take a short look into how we see the scaling challenges of the future in quantum computing. And when you look at these high qubit numbers, a lot of people always talk about, let's say, a system of 1,000 qubits, maybe even 10,000 or 1,000,000 qubits. Very often, I would say that's a lot of speaking about things which are about the future. Let's talk a little bit more about now. And what we believe now still is really needed is a lot of people still focus on qubit technologies. So people want to improve their coherence times, they want to look into new qubit architectures, and that's why we believe we still have to provide solutions for those people who really worry about, let's say, signal stability, phase noise, output noise, and so on. So for these, we provide solutions that can support this research regarding qubit technologies. And when we really go to higher qubit numbers, at the current time, what we have to look at is hundreds of qubit systems. Because people will get to work quantum error correction codes on these systems, and we have to take the learning from these hundreds of qubit systems then to really scale up to higher qubit numbers. And what we believe in is, for these hundreds of qubit systems, we will need the right control system architecture. We will need a proven and dependable hardware solution. And also, we believe that what is needed is a scalable software solution. And in the rest of the talk, I would like to give you, to all those three topics, a good answer why we believe that this is, let's say, the technology we provide and why this really solves these scaling challenges. Now let's take a first look at why system architecture. So this is an example of our newest released instruments. It's the so-called Quantum Hub. And what the instrument does, it does a synchronization of all different channels and instruments used in a much more complicated setup. What it can also do in this star-like architecture, it can provide, in the end, central knowledge of quantum qubit readout and distribute that knowledge through the whole system. And this can provide a feedback latency of 550 nanoseconds measured from last sample in and first sample out. And last, if you really want to scale up with this solution, then this can control up to 488 channels and 448 channels. And it can also be used in now not a star-like architecture, but you could have a star of stars and then use this to scale up to 1,000 qubits. Now, the second topic I was emphasizing before on was proven and dependable hardware. And one way to prove that is to really measure how stable are the signals. And what we have done in this experiment here, we put two instruments racks next to each other, distanced by 6 meters, synchronized with our central controller synchronization unit. And we have measured over 14 days how stable the signals are. So how much skew is between, let's say, the rising flank of two output signals. And we could measure over those 14 days, we could have done the measurement even longer, but we thought, okay, after 14 days, the point is kind of proven. We could measure that the skew inter-instrument is only 150 picoseconds, intra 50 picoseconds, and the standard deviation is only 20 picoseconds over those 14 days. And this really shows in the end, not only how proven and dependable this hardware is, but all this solution in the end comes out of the box for the time and frequency synchronization, the distribution of the measurement results. And what that means is, as a customer in a lab, you don't need to calibrate those systems. You just connect the cables, and directly we can guarantee this proven stability on the instruments. Now, there was the third topic I was already emphasizing on, and I've been talking about hardware, I've been talking about the system architecture, but I have not yet been talking about how to now really control these instruments. And one can say hardware is nothing without control. So the solution we provide here is Lab1Q, which is our software framework that really provides the user the ability to control and program the instruments. And I'm starting with a very easy example just to illustrate the intuitive programming. So you see here an easy example of programming a Ramsey experiment. And what you can do there as a user, in the end, you can just use this line of code to play a pulse signal on one of the output signals. You add a you add a delay in between and have another output signal. So that already constructs your Ramsey experiment together with a measurement, and then also together with some kind of looping or sweeping ability, this altogether constructs the Ramsey experiment. And what's important to note here, we always guarantee sample precise 100% runtime control and predictability, that you can control your parameters in real time. And also it's important to note that our software is released under an Apache license. But when we go to more complicated examples, a user really has to think intuitively and write the code at the same time. So one way to really support users here is by pulse sheet visualization. So what you can do here in this more complicated example of a Surface 7 code, you can not only program directly on the instruments, but we can also visualize all the pulse sequence a user really wants to do and use. Or even more complicated examples, let's take a look at active qubit reset. And many of you will know, if you really want to do these experiments, this can get really complicated. So people need to know HDL coding, for example. And with the solution you see here on the right-hand side, these are not many lines of codes which you can directly use for active qubit reset. Or repeat until success, another solution which many people use in the community. If you want to do, for example, magic state distillation, then also those lines of code are all you need to prepare these kind of experiments. Last, there's also a way to interface now with other software frameworks. And a lot of people in the community use OpenQASM as a standard. And what we can do, and I would also like to demonstrate you that if you come by at our booth, What we can do is, you see here the programming of the circuit in the OpenQuasm. We can transpile the circuit into our software framework. We can also simulate the output, as you can see here. And then you can also see those pulses directly played on the instruments. And as I already said, if you want, come by at the booth and we can demonstrate this feature to you. Now, I want to switch a little bit from what I've been saying about reliability, the system, and also the software. I want to switch a little bit to, let's say, a Korean view. And here I would like to share two success stories. First success story is from SKKU. And what you can see in this success story, and thank you very much, and an acknowledgement to Yonok Chong and Yongdu Kim, what you can see in this experiment is a VQE type of experiment. And these experiments, they are really hard to do because you need to do and have very fast update of the waveform data in your algorithm, you can say, or maybe, let's say, in your experimental setup. And this example here is just, let's say, a proof of principle example of a VQE experiment in which a hydrogen bond was calculated. And this sort of combines all these different software solutions, which I have shown you before, in this way that you can really define again the circuit in OpenQuasm. You can update the waveform data very fast. And with these fast updates, you can then really rely to do VQE in, let's say, a reasonable amount of time. Second success story from Korea is this with Chris. So the challenge here from Chris has been they want to ramp up very fast. They want to focus on the engineering on their side, and the challenge was that they really wanted to be able to do a live demonstration of their 20-qubit system at the K Quantum Square meeting at the beginning of this year. And anyone in the room will believe me, a live demonstration on a 20-qubit system in a conference situation, that's a hard task to solve. But they were able to do so, and we are very happy here, and acknowledgements there to Dr. Lee and also to Dr. Hwan Sop. And as I have been saying, in that live demonstration, they showed a 20-qubit Rabi measurement, 10-qubit IQ blobs, 5-qubit X gates, 7-qubit H gates, and so on. So all of that live. And as far as I know, also if you would Google for this, there might even still be a video out there you can watch. Wrapping this up about Korea, I'm very happy to announce today two new collaborations we have in the Korean community. So first of all, today we have signed a memorandum of understanding with Norma. You all know it's a Korean software company. And in this collaboration with Norma, we will focus together on a software interface between their software solution, which is focusing on the application side, and our software solution, which is focusing on the instrument control side. And together in the Korean ecosystem, we will then provide solutions that focus on Korean customers. The second announcement is about an MOU and a Memorandum of Understanding together with KAIST, and actually it's the Graduate School of Quantum Science and Technology at KAIST. And this will focus on teaching or developing teaching programs for students, graduate students from KAIST. And in the end, this will help to develop, let's say, the next professionals or the next generation of quantum computing professionals in Korea. And we are very happy about these two collaborations because they show, together with our already existing success with our customers, our dedication to the Korean ecosystem. Now, to summarize everything which I have been saying in my talk, first of all, we believe that our technology is the leading hardware technology to provide the right solutions, especially when it comes to scaling to larger qubit numbers. That we have a very intuitive and scalable software solution, and our system architecture is very much future-ready with this star-like architecture. For our partners, it's very important to know we have a local Korean subsidiary. So if you come by to our booth, you will also meet our Korean colleagues to talk to you. For academia, we focus on the cutting-edge research, and for companies, we reduce the risk, time to market, and also the capital requirement if you really want to scale to large systems. With this, I would like to invite you to come by at our booth. It's very easy to find. Honestly, I forgot the number, but it's very easy to find because it's just behind the stage here. Yeah, so if you just turn around, you will find it there. And in the end, I would like to thank you for your attention.
네, 맞습니다. I'll give you a detailed number. It's 706.
Thank you.
네, 자 S06번 방문하시면 취리히 인스트루먼트 방문하실 수가 있겠습니다. And for the case of they have question, let's have a short Q&A. 자, 혹시 질문이 있으신 분들은 거수해 주시기 바랍니다. 네, 자 앞쪽에 마이크를 전달드리겠고요.
Thank you for your lecture. It's the beginning stage of quantum computers, and if I can imagine that there are multi-process internally together, you introduce the scalability using outside device. How do you expect the future of the multiprocessing in quantum computing?
You mean like multiple QPUs?
Yeah, yes.
Yeah, okay, thank you. That's a very good question. So actually we have a project on that. We even have 2 projects on that. So we used to have a project, I don't know if you know this, so Andreas Wallraff at the ETH Zurich, they have established a quantum link between 2 fridge and 2 QPUs over 30 meters. It's actually used for proving loophole-free bell test experiments, but you can also use it to prove quantum computing over a distance. And we have a follow-up project together with that group, and this follow-up project now focuses on using multiple QPUs in one fridge. So I would say for sure that's the future, and maybe if you've also looked at the IBM quantum roadmap, so for sure this is one of the futures that I would also envision, that we need to be able to control multiple QPUs and connect them. Still a lot of problems to solve, how to connect QPUs and so on, what's the link then and so on, yeah, so not easy task, but for sure this is the future.
네, 맞습니다. 자, 혹시 더 질문이 있으시다면 거수해 주십시오. If you have a question, please raise your hand. 네, 앞쪽에 남성분께 마이크 전달 드리겠습니다.
Thanks for your talk. And I wonder, you emphasized one of products that named Q-Hub, which is star architecture, you said?
Yes.
Why is it so important in your older products? Could you explain more detail?
You mean why in general it's so important, or why it's important to have a star-like architecture?
Yeah, the second one.
Oh, okay, the second one. Yeah, so that's what I tried to say before, that in the current setting of, let's say, 100 qubits, it's very important to keep the information about, let's say, the whole QPU state in a central located, let's say, instrument. Yeah? And by keeping it central, the information, then if you think about quantum error correction, and especially real-time quantum error correction, you can then make sure that you can prove to be able to do quantum error correction, implement the decoders and so on within that full system. But this also maybe goes back a little bit to the question of the gentleman before. If we think about the future, then we have to think more about tiled codes, for example. So let's say quantum error correction within certain units of a QPU. But this, we believe, will only really become necessary and possible if we go to even larger qubit numbers. So let's say to 1,000 and so on. So that, as an answer to your question, for the time being, keeping it central with the hundreds of qubits is the best solution still. If you go to larger systems, you have to solve a lot very complicated engineering problems. How to synchronize and keep the information over the whole system if you have more qubit numbers.
네, 고맙습니다. 자, 시간 관계상 여기에서 Q&A는 마무리하도록 하겠습니다. Due to time limits, we conclude the Q&A session.
Thank you.
고맙습니다. 자, 다시 한번 발표해 주신 우리 취리히 인스트루먼트 모리츠 키르스테님에게 큰 박수 부탁드리겠습니다.